So now that we've looked at the relationships of pressure, volume, and temperature sort of independently of one another, remember that we always sort of kept something constant. We kept temperature constant, or pressure constant, or volume constant, in order to just look at the relationship of two of the variables. But we know that they are all intertwined with one another. So that's where we get the combined gas law, that pressure times volume over temperature is equal to pressure times volume over temperature. And if you notice, if you just cover up one of the variables, like if we covered up temperature on the bottom here, then we have P1 times V1 equals P2 times V2. That's Boyle's law. If we covered up the pressures, then we'd have Charles' law. And if we covered up the volumes, then we'd have Gay-Lussac law. So they're all in here together at once. And so let's do a problem in which we combine all of them. Okay, so again, remember I said in your reference table you have the equation. So it's right here, and if you were to cover up the T's, then you'd have the Boyle's law. If you covered up the V's, then you have Gay-Lussac law. If you cover up the P's, then you have Charles' law. So all of the laws are there for you in the combined gas law. So let's do an example of one. So you have a research submarine, and it's at a volume of 1.2 times 10 to the 5th liters, and it has an internal pressure of 1 atmosphere and an internal temperature of 15 degrees. If the submarine descends to a depth where the pressure is 150 atmospheres and the temperature is 3 degrees, what will the volume of the gas inside the hull of the submarine be? So let's go ahead and define our variables. So I'll just write it out so we can see here. P2, V2, and T2. So pressure 1, so the initial pressure is 1 atmosphere. So P1 is 1 atmosphere. V1 is 1.2 times 10 to the 5th liters. And my initial temperature is 15 degrees, but remember I need that in Kelvin, so I'm going to add that, so it'll be 288 Kelvin, right? So then my pressure 2 increases to 150 atmospheres, and my volume is what I'm trying to find. So I'm trying to find my V2. And my temperature I know is going to drop to 3 degrees Celsius, which is 276 Kelvin. So when we look at this, it's a lot more difficult to sort of conceptually think of this because there's multiple things happening at one time. So let's just go ahead and plug in and do our algebra. So we want to solve for V2. So the first step that I'm going to do is I'm going to multiply by T2 on both sides. So I'm going to get T2 P1 V1 over T1 equals P2 V2. And then I'm going to divide by P2 on both sides. So divide by P2, that will cancel, and I'll have P2 here. So I'm left with T2 P1 V1 over T1 and P2, and then V2 over here. So it's important that we keep track of our subscripts. And so let's go ahead and plug in the values that we have now. So temperature 2 was 276 times pressure 1, which was 1, times volume 1, which was 1.2 times 10 to the 5th. All divided by T1, 288 times 150. All right, so remember, if the numbers are on the bottom, we divide them. If the numbers are on the top, we multiply. So 276 times 1 times 1.2 e to the 5th, and then we divide by 288, and again divide by 150. Now I could multiply these and then divide by the whole thing, but just be careful, you don't want to divide by 288 and then multiply by 150. That would have to be in parentheses there. So I get 766. So that's 766, and I was solving for volume, so that will be liters. So this is just an example of a combined gas law where we're looking at all three variables at the same time.